welcome to this progress report on our project on machine learning observables from single-shot measurements of many-body systems. Yeah, there's two ends to the content of this talk. One is like simulating many-body systems on a computer. We are using cold atoms, and we use the multi-configurational time-dependent hard tree method to solve their Schrödinger equation. And then we also simulate the measurement of these many-body systems. And the conventional measurement is done with so-called single-shot images, which is almost literally photographs of the quantum many-body state. And these photos, they are distributed according to the many-particle probability distribution. And now we are going to use these photos as the input data for machine learning algorithms and try to see to which degree of accuracy or how well we can extract observables from them. So I'll start with acknowledgements. First of all, for the contributions to the machine learning software and the MCTDH-X software, I want to acknowledge Paolo Molinini, Ray Lin, Luca Papariello, Marius Tsatsos, and Frank Schäfer for coaching our machine learning endeavors, and for the funding and of myself and the computations. I acknowledge these institutions here. So here's an outline of my talk. I'll give you a brief introduction to the physics and the theory that we are applying to describe the physics. Then I'll give you background on ultra-cold atoms and machine learning. This is going to be somewhat superficial regarding the theory that we use to describe these systems, because, okay, I guess for everyone listening, machine learning is rather the new part, so I try to go into more detail with that. And then we'll have some results and conclusions and outlook. Probably I should already start here with a disclaimer. It's a progress report, so the results are incomplete, especially because some of them are on the clusters that are currently closed down. So, but okay, in any case, if you have any questions, please interrupt me, ask, and I'll try to answer them immediately. Okay, so I'll start with ultra-cold atoms. So why are these so interesting? Basically, they are a uniquely tunable subject, and as a theorist, it's cool to study them because you literally can study whatever you want. There's a way to realize it with ultra-cold atoms, and so essentially the Hamiltonian is known, and we can control all terms in it. We can control the interparticle interactions, and we can control almost at will the trapping potential. So this renders them an ideal tool for quantum simulation. So we can make them, the ultra-cold atoms, mimic condensed matter systems, like Hubbard models or the physics of superconductors or the like. And what's most important for this talk, we can also measure them very nicely, maybe in projective measurements of this many-body state psi in what we call single-shot images, which is basically taking a photo of the sample in the lab. And I've pasted in this slide an example where the group of Ian Spielmann realized vortices in a BEC by applying an artificial gauge field to them, and this can be seen as a quantum simulation of the physics that you would expect in a type 2 superconductor with a magnetic field. So, and it's really okay. I mean, in these images, there are random samples of the many-body density. So there's all observables, all possible few and many particle observables are in principle in there, and the particle fluctuations are directly visible as fluctuations from image to image, and we want to take them in this project, in this talk. We want to simulate them with MCTDH-X, and then we want to apply machine learning algorithms to them as data and extract observables from them. So you might ask why, because when you compute the wave function, you actually can extract all the observables already from this computed wave function. But the aim here is to attack the experimental problem, because in experiment, people don't have access to the wave function, so they have to rely on extracting their observables from the images, and we want to see whether we can improve on the standard ways of dealing with these images by applying machine learning algorithms. So without further ado, I'll start to introduce the multi-configurational time-dependent R tree for indistinguishable particles theory. The generic Hamiltonian that we consider is containing one-body terms, this small h here, and two-body terms, this w here. The one-body terms usually contain the one-body potential and the kinetic energy, and the two-body terms usually in this talk, where we consider bosons, is contact interparticle interaction potential. So with MCTDH-X, we use an ansatz for the wave function, which is such a configurational expansion, where we have coefficients and configurations, and both are time dependent. So we build the configurations from a set of time dependent single particle states or orbitals, and we weigh these configurations with time dependent complex valued coefficients. And then we plug this ansatz in a suitable variational principle and perform a variation with respect to all parameters in the ansatz, which is with respect to the coefficients and the orbitals. So pictorially speaking, MCTDH-X can be pictured as a way to break down a high-dimensional complicated object, namely the wave function, into sums of products of lower-dimensional computationally manageable objects, namely orbitals. So I wrote down the action here and its variation. I will spare you the equations of motion. If you want to discuss them and the way we solve them in detail, we can do that later on. But so let's come now to the machine learning background, so to say, for this talk. So I should actually say here that all we do, all that's going to be in the talk is so-called supervised learning, where we take as a ground truth the observables that we can extract from the solutions that we compute from the wave function, and then we use these exact observables to train our machine learning algorithm to extract them from some data which is not the exact observables, namely the single shot images. So yes, let's briefly elaborate what a machine learning model is. So basically, it's inspired from biological systems, from neurons that are organized in layers, and they are interconnected. And typically, we are aiming at finding a model that is parametrized, that should predict something. Let's call the model F. Let's call the something Y. And we have a data set X, which is the data from which we want to predict our Y. So we are looking for a function with potentially many model parameters, which gives us this Y from a data set X. This talk we are going to discuss models that infer physical observables, Y from single shot simulations X. Now, for some slang that I already used, that is common in machine learning. Usually the model parameters are referred to as weights and biases, and the architecture of the model, like how many layers of neurons do we have, how many neurons are in that layers, this is summarized as hyperparameters. And then training a model basically means that we have some type of target function or goal loss function that we try to minimize. So for the example with observables, we have an exact observable that we compute from the wave function, like the density or whatever, and our loss function then usually is the mean squared error of our prediction. So the mean squared difference of the prediction to that exactly computed value of our observable. So then, in order to validate how well or not well our model does for the current set of hyperparameters and model parameters, we do validation. We show data to the model that it hasn't been seen before. So data that we kept aside before training the model, and we use this data then to validate whether the model does predict the observables correctly for new data. So let's go through the building blocks. So I mentioned neurons. What is a neuron? A neuron computes a weighted sum of its inputs, which are these x's, and they are weighted by weights W, and it adds to this weighted sum a bias B. And then it has an activation function, which is applied to this weighted sum and decides whether this neuron is going to output something. And yes, okay, basically this is a simplified picture here, because each neuron, of course, then has connections to potentially many other neurons. So it's not necessarily a single output. So that's probably because why there is a head on the Y. And okay, some commonly used activation functions are shown here. I don't want to go through the details actually. I mean, in all the models that we are going to consider in the remainder, I think it's going to be rectified linear units, this value. Now, here's an example of such a model, which is actually it's two models, one on the left with a single output and one on the right with multiple outputs. So these models, these architectures are actually the ones that we used to obtain some of the results that we will show or discuss later. So the input size here is 25,600 neurons, because we consider here a stack of single shots of 100 single shot images, and each of these single shot images has 256 points. So that makes that number. And then we have a layer of 512 neurons, and these are in these so-called multi-layer perceptrons. All neurons of one layer are connected to all neurons of the subsequent layer, and so forth. So there's a lot of model parameters here actually. So in like the number of model parameters just connecting the first layer to the second layer would be 25,600 times 512, and then again we add 512 times 256 and so forth. And in the end, okay, here in this left model, we have a single output neuron that would then give us a prediction about a single valued like scalar observable. For instance, we applied this model to predict the particle number in some single shot images, or we used it to predict the fragmentation, which is the first eigenvalue of the reduced one-body density matrix. So when we want to do a so-called regression, where our output, like the observable, is, for instance, the density, which has a spatial dependence, we need more output neurons. So if we want to make a regression for the density on the spatial grid, which has 256 points, then we can train the model to predict from these 100 single shots 256 real values, which then correspond to the values of the one-body density on the grid. So we can iterate on that later on. So good. This is what I included regarding so-called multi-layer perceptrons, which are layers with dense connections in neurons. And now the second type of architecture that we use are convolutional neural, so-called convolutional neural networks. Here the neurons are not densely connected between the layers. So the neurons are replaced by the weights are replaced by so-called filters. And these filters have a certain size. In this example that I show here, it's a 3x3 filter. And yeah, okay. Thanks to Luca for providing these images. So it's a 3x3 filter, and we are convoluting this filter with every possible set of or subset of numbers in our grayscale image, which is shown on the left. And with that, we get an image of a reduced size on the right. So what that means is we really put this filter on top of our image and multiplying component-wise the values of the filter with the values of the image and add them together, and we'll obtain this number. Then we shift it by one. Okay, there's also the option to shift it in different strides, but okay, for the sake of simplicity, we shift it by one, and we obtain a different number, and so forth. And we obtain an image of a reduced size. And okay, the parameters that are now learned, so to say, the weights are now the entries in these filters. And the idea is that by having many different filters, we can, so to say, extract different features that are, or different types of information that are contained in our original image. So here's an example of a convolutional neural network that we used in the results that are going to follow. And so it's not only a single convolution. There's different operations in between, which are pooling operations. That basically means that we have generated a reduced data size by applying our filter to the image, our filters to the image, and then we take, for instance, the entries in this reduced image and say we are just interested in the one which has the maximal value. In that case, this would be the 8 on the top right. That would then correspond to max pooling, so-called max pooling, which is shown here as which enters here as an intermediate layer. So let's go through this quickly. We have 3 layers in total, 3 convolutional layers and 2 pooling layers in between. So the input data again is an image of 256 points and 100 times such single shot image. We feed this. We create. We have a convolutional layer with 256 filters. And then we do max pooling. We convolute again with 256 filters. and then we convolute again with 4 filters only. We max pool, we flatten, and we get an output. And on this, so flattening basically means all the remaining numbers that we have are taken as a line, a linear line, and then from these, you can read it. It's 484. We drop out a certain number to get our final 256 or 256 squared prediction. So remember, I mean, the output layer has to correspond to the size of the output layer has to correspond to the size of the observables that we are aiming at. If it's a single scalar, then we would even have only a single neuron here. So all the 484 in this last flattened layer are connected to only a single output neuron. If we have a density here, it's 256 neurons with real valued weights. And if we have a correlation function which lives on the square of the grid, we would have 65,000 output neurons here. And then this is somewhat starts to be prohibitively large because the number of parameters that you have in your minimization problems scales with this number of output neurons. But there's ways around. We will discuss that later. Yes, so this was a run through the convolutional neural networks that we use to obtain our results. Yeah, and now I created some like wrap-up slide for the machine learning life cycle that we follow through. So basically, we used MCTDH-X to generate our data, and then we pre-processed and pre-processed it. And okay, in order to make it compatible with any type of neural network or artificial neural network that you want to train, you have to reshape it to feed it to it. You have to tentatively clean it. If there's some data that you actually don't want to pollute your training process, then you can omit it. This is rather important for experimental data later on. And then in order to obtain a model, you iterate these three steps. So you set up a model topology, then you train the model by minimizing the loss as a function of the model parameters. Okay, here I give the mean squared error loss, which we typically were using, and then you validate it and see whether it actually does sufficiently well for your desires on a data that it had not seen before by then. So yes, so this iteration process of these three steps, that's called hyperparameter optimization and can be automatized. And we did that already using this HpBandSter package, which is conveniently available. But the results of this hyperparameter optimization are stuck on Linux, so they're not part of this project. So let's come now to the results. Finally, I'll first describe the data set that we used. And for this, I introduced the Hamiltonian. So we considered one-dimensional bosonic particles that are interacting with a contact interparticle potential, and all of them have a kinetic energy, and the double well potential in which they are trapped is modeled as follows. So we have an external parabolic confinement, which just basically an harmonic oscillator with unit frequency. And we put a Gaussian barrier in the middle, and this Gaussian barrier has some height h and a width sigma, and we put additionally a tilt to make the problem asymmetric. this is just to generate, to make like a variation of the states that we are getting out a bit larger. And yeah, so the parameters that are given in color here were used, were generated randomly. So namely, we randomly generated n, h, sigma, alpha, and lambda 0. And then we ran MCTDH-X to generate a ground state wave function in this problem that is defined by these 5 parameters. And then for every ground state, we generated 1,000 single shot images. We generated the observables that we want to look at, the reduced one-body density matrices, the reduced two-body density matrices, the density, of course, the potential, and so forth. And yes, so this is basically the data set as the data from which we want to infer things. We will use the single shot images, and as the data which we want to infer, we will take these observables. So what are those single shot images? They're samples S1 to Sn, which are either positions or momenta. So the results I'm going to show are only for positions that are distributed according to the probability that is given by the wave function absolute value squared, which is an n-particle probability distribution. So all correlations and fluctuations are in principle in these images. But in order to reconstruct completely this high-dimensional probability distribution, additively very many images would be needed. So if you're aiming at reconstructing a two-variate function like a correlation function, then usually in an experiment you will need many images. And our aim now is to reduce the number of those images by using a sensible model, yeah, instead of a not so, let's say, sensible brute force way of evaluating it with a formula. And to illustrate a little what are those single shot images, I just picked one parameter set, which is basically one specific double well that is tilted slightly and has a certain barrier width and barrier height, a certain interparticle interaction, and a rather small particle number here. And okay, I picked a small particle number because then you really can see fluctuations between the different images very obviously. So I plot the 3 single shot images here, and I plot the density, which basically is which you would obtain by averaging many single shot images. I put in total 9 of them. So if you focus now on the 3 lines on the bottom, there's really randomness in them. Yeah? If we look at different samples. So in every single measurement that we take, the particles are going to be detected at different positions. And this is because, okay, first of all, they are correlated, they are interacting, and they are described by a probability distribution. Their positions vary. Now let's come to the observables that we are going to look at in the following. This is mainly the reduced one-body density matrix, which is given here as an expectation value with field operators, or respectively in a basis set, or as a trace operation on the many-body wave function. So, and I mean, this trace operation is basically where we try to win with our model as compared to just averaging images, because here we trace over a lot of degrees of freedom, so we are not really taking into account that information to compute the quantity. Okay, we are not taking into account all of the information. We're just tracing over it in order to compute the quantity on the left. Maybe by somehow intelligently taking it into account, we can get the same information out with less images, so to say. So the diagonal of this reduced one-body density matrix is just the one-body density, or just the density. And similarly, we can look at the two-body reduced density matrix, which is also given as an expectation value of a product of field operators, or alternatively as a trace operation, or alternatively when you use a basis set to represent it by this quantity. And for the two-body density, we're for illustrational purposes are going to restrict ourselves to the diagonal, which is a two-variate function, or we call it two-body density, where this x prime, these primed arguments x1 prime and x2 prime are equal to the unprimed arguments. So as a kind of sanity check, we applied a multi-level perceptron model to infer the particle number from single shots. In principle, that just amounts to computing the norm, which is okay. You actually only need a single shot to do that, and it should be in our simulated measurements. It's exactly the same value for every picture. So and we find that okay, all values are falling nicely in this plot down here, which compares the predicted value for the particle number with the actual particle number. All values nicely fall on the diagonal. This means that there's after some epochs of training, which means steps in the minimization routine that was applied to minimize the prediction of the model with respect the error of the prediction of the model with respect to the particle number that you know, there's practically no error anymore. And so this error histogram down here shows that at most the predictions are wrong by 1, plus minus 1, which is fine, I guess. So then we went on to infer the density. So here, this is the second multi-layer perceptron that we applied, that we are now using. So we have 256 output values, and again, like the errors in the validation at a loss during the training, they nicely converge to a value close to 0, and the predicted values for the density on the grid are very nicely corresponding with the actual values. So yes.
So you're still randomly choosing the parameters at the end for every single time you produce is 1000.
Yeah, I mean, yeah.
And this is basically, so you do it. And what I wanted to ask is, so how big is the sample? So how many particles do you have there typically? So what are
so the particle numbers were chosen randomly between I guess 2 and 100. So and we have 3000 wave functions as a data set, but this particular training was done on a subset of those. Like we only used something like 1000 wave functions to train the model, because otherwise it's takes prohibitively long on our desktop computers, and the good results they are stuck on the clusters. So I mean, how this works is basically you partition those into the data into batches, and for every batch, this algorithm evaluates an approximation to the gradient and does a step like the gradient type of gradient descent approach to minimize the error for the prediction of the density in this case, with respect to the density that we computed from the wave function. So, And this plot down here, that this D, it compares the actual and the predicted values, and you see, okay, it works nicely. So we also we are going to look at samples in a minute, and what I wanted to point out here is that actually these errors in the validation that we have here, they converge to something just below 1. Okay, so the prediction of the model, and this is basically in number of particles. So the prediction of the model is on average wrong by 1 particle integrated over the whole grid. So it's fairly good, but we also used 100 single shots in this case, which is quite a lot. And now, I mean, this has to be compared with a conventional way of evaluating the density from experimental or simulated experimental data, which is an average. Okay, you just take the number, you just take your images and you average over them, and the marginal that you're going to get in the limit of a large number of images is the density. And this we applied here. This is a plot that plots the error of approximating the density just as this average of single shot images. And I guess, okay, there's error bars in here because I used 400 wave functions. So like 400 points in my data set of 3,000 were used to evaluate the error with this function. And you see that this, as a function of the number of single shots per image, converges to something around 3. Okay. When I have 100, I get 3. Whereas when I use my machine learning model, when I use 100, I get something below 1, which means that effectively using the same amount of data, I get the same information for less images. Okay, and this is okay. I mean, for a theoretician, because when you solve the Schrödinger equation, you can actually compute the density exactly. You don't care about this, so this is not so important use for us. But for experimentalists, I guess they are going to be happy, because if they can run their apparatus more efficiently by getting the same information out of their experiment with in smaller time, then this is good news. Good. Let's continue with the next observable. So I split this. I forgot to say that I split the results into observables where you have a conventional formula, and there's also observables where actually there's no way of obtaining them straightforward, which is the potential which is in the Hamiltonian, something that you cannot straightforwardly evaluate from these single shot images. But with a machine learning model, as we will see later, you can. So here's some examples which are just more or less randomly picked from the direct comparison of the model prediction and the ground truth that we computed from the wave function. You can see, okay, what you actually saw on the previous slide from the error, they match up quite nicely. So there is, although there are some problems here that you can improve on, namely in some places it goes negative and it overestimates or underestimates, makes some additional wiggles. But generally we were really happy when we got those results. So now for the two-body density matrix, I introduced it before. So what you can see here is a loss, which is basically during the training, how well the error is minimized on the training data set, and then on the right there's the validation data set. The absolute values here on the y-axis of the error are larger because we used an unscaled or unscaled data, and the two-body density matrix is n, like it's normalized to n times n minus 1, so it just has large values in some cases. Now you might say, this error 200 is large, but this function has values which reach out to 2,500 in some places, so it's not too bad. So you can the number of particles is between 2 and 100, so on average 50. So so in essence, also this worked quite nicely. The error histogram here is probably something that was not so properly evaluated. So sorry, progress report. But so here are, so this plot actually took the longest time to generate, because it contains 1 point for every grid point in every prediction. So, and then every grid point in one prediction is 65,000 values, and I guess all predictions here was something like a few thousand. So it took a long time to visualize this. Yeah, and also for the two-body density matrix, the diagonal of the two-body density matrix, there's a formula to evaluate it, which is given here, and we checked what errors can we do we get if we use this formula to evaluate the two-body density as a function. And here again, it's plotted as a function of the number of single-shot images that we use here in this approximation as n shots. And you see for about 100, like for 100 shots, we get something around 350 here as an error. And in our non-hyperparameter optimized convolutional neural network, we get something that is between 100 and 200. So we also decreased the amount of pictures which is necessary in order to obtain the same amount of information. Of course, okay, this is just 1 point now. We just evaluated the model using as input a stack of 100 single-shot images. So, and here we use many different numbers of single-shot images to extract that error, because it's way faster to evaluate this approximation than to train a neural network and to evaluate the quality of its predictions. But okay, eventually, when we again go back to our clusters, we are going to add another line here. How well or by how much can we improve for a certain number of single shots the prediction for the two-body density? Okay. So now let's continue by looking at some example plots. So yeah, the two-body density is a function of two variables, and this shows how well the neural network did on four samples. So you can see that overall it works quite nicely. There's still some differences. For instance, here we have some contribution that is on the off diagonal that in the actual computed two-body density are not present. So there's room for improvement. We are working. Now we're coming to observables where there's no formula to directly evaluate them from single-shot images. And the first example is something I'd like to refer to as reverse density functional theory. So we're trying to infer the one-body potential from a set of single-shot images. And as you see, this also, like the prediction error of the model, quite nicely converges to something which is close to 1. You cannot see it from here, but take my word.
What are you measuring? Not trying to measure the
So the input data are these single shot images, like the positions of the atoms that you image, and
you are trying to reproduce the potential.
The double well potential.
Okay. And what is the parameter? So the height of the potential, or
no, the whole potential as a function of
okay.
the whole potential on the grid, 256 real values. And okay, you can see that this this works quite nicely too. Yeah, the errors are like on the grid are mostly around 0. Some of like the largest error are maybe 5 in a few instances where that's around 10. Okay, and if you look at that plot, yeah, it seemingly works very nicely. But I want to point out that there is values around like around these small values of the potential where it doesn't work so nicely, and this is problems in predicting the values of the potential at the barrier. So this tentatively can be improved. Let's look at some examples. Here we don't have a comparison with an error that we got from a formula, because there is no real formula. And in these examples, you see that yeah, the predictions, okay, at the edges sometimes goes wrong, and at the center sometimes is not so good. And the reason for that is that usually there's no atoms detected there, so they don't go to places where the potential is large. So you cannot really reliably infer the value of the potential. You don't get any.
So it would be solved if you just increase the number of particles.
It might be, yeah.
What is the range of interaction strengths?
I think it was between. Okay, that's difficult to say something physical here. So it's far away from where you would get something like a Thomas Fermi profile. So they are rather weakly interacting bosons. The numerical values that we used were between 0.01 and 0.15 or 0.2, if I remember correctly. So they are at 100 particles. This is still rather weakly interacting particles. I mean, you wouldn't expect anything like Tom-Girardot type of behavior, like fermionization, when you go to infinite interparticle strength. It's far from that. So this is for the one-body potential. Tentatively also very interesting for experimentalists, because although they have quite a well-controlled setup usually, so they know the magnetic fields, and they know from their laser configurations what is the potential that they exert on the atoms. But yeah, there's always limits to the accuracy of that prediction, and I guess by applying such a model to experimental data, it could improve on that. Now let's go further. Let's try and infer the reduced one-body density matrix. So not only its diagonal, the density, but the full matrix with the off-diagonal terms. And also here we get so ignore this bottom left part, but we get quite nice convergence of our model minimization, error minimization, and the error levels off after 30 epochs of training at something like 150, 200. And you see that the actual predicted values coincide quite nicely with the actual values, besides the places where the actual values are large. Then somehow the predicted values are too low. This is why this thing here bends a bit like a banana. But so let's look at the examples. They quite nicely agree. Okay. Somehow it seems that actually the off diagonal is where the predictions usually would not be so accurate. And this is something that, yeah, I mean, the off diagonal, strictly speaking, is not straightforwardly accessible just by taking the images. This has to be extracted from the network from the fluctuations of the particles. So it's somewhat reasonable that the predictions are off there the most. But overall, the pictures actually quite nicely agree. And this is something nice. So the next result is inferring the fragmentation, which is the first eigenvalue of the reduced density matrix. And yeah, again, okay, you manage to obtain somewhat reliable prediction, which is still, say, fluctuating quite a lot, but you can see the tendency that these values are rather on the diagonal than off the diagonal. So we hope that we can improve on that, but we didn't get the chance yet to apply the convolutional neural networks to that case, which usually have an even better performance. I pick one of those, which is the inference of the two-body momentum space reduced density matrix. So, and we infer this quantity from real space single shot images. So in a lab, this corresponds to two different measurement camera setups. Okay, when you want to change from one to the next, it tentatively takes a month or so, and still it is possible to extract from real space single shot images momentum space quantities. And here we do that with a two-body reduced density matrix, or the diagonal, the two-body reduced, the two-body momentum density plot. And you see, okay, I must admit, this is a training that I did yesterday on my desktop computer. So I reduced the number of data sets here to 500, and the number of single shots is 100. But still, I managed to get an error of around 400, and also the validation error is on the same order of magnitude. Sadly, the version of our current software package that was used to generate that did not output this histogram and a comparison of the predicted and the actual values for all values on the grid, but I generated some samples. So this is actually astonishing. Again, I mean, okay, the error on average is twice as large as when we do it for the real space momentum, the real space density matrix, but still that you get at all a result that is accurate is highly promising. And here are 4 comparisons. So yeah, it's a bit hard to see, but the absolute values are off in some places, but the general structure is quite well reproduced. And okay, I mean, in some cases like this one, there's an additional feature which is a minimum at k and k prime equal to 0, which is artificially introduced in the prediction. But I guess with more data and improved model architecture, we are going to also solve these problems. So this was the last results. Now I'll wrap up. So as I said, the results are quite promising, and especially this last example where we infer momentum space quantities from real space single shot images is a nice and surprising step, actually. When you do the optimization of these architectures of the neural networks, artificial neural networks by hand, it's really tricky, and it's sometimes very non-obvious how these hyperparameters actually affect the quality of the output, and this can be time consuming. So one imminent further step, and that's now the outlook, is going to do some automated hyperparameter optimization, which is, as said, available, for instance, in this HpBandSter package that people from Freiburg actually developed. Then what becomes prohibitive when you predict these matrices, like the two-body correlation function, is the output layer size. Because again, I mean, you need, when you want to predict in this brute force way that we presented now, when you want to predict the two-body density on the full grid, you need 65,000 output neurons if your input has just 256 pixels. And we were contemplating to use an interpolation. So the neural network would actually learn an interpolation of the data that it should infer, instead of learning its value on every grid point. So, and the number of parameters in the interpolation is of course much less, so we can decrease the output layer size, make the problems more manageable. And then of course we need to benchmark the accuracies of the predictions that we make more thoroughly. Now I only presented comparisons basically for a single data point. So the predictions that we had shown were all for 100 single-shot images with the neural networks, whereas with the formulas we had errors for a range from 0 to 100 single-shot images. We should also run or train our models and compare their accuracy for different number of single-shot images. And then, of course, once we are even more sure that this works out nicely, we should be starting to apply or consider applying our machine learning tools to experimental data. So with that, thanks for listening. And if you have further questions, please ask.